Now, okay, so we're starting trig related rates. On the board is our first example, and just as a quick review of related rates, remember with related rates, you always write down what you're given, you write down what you're trying to find, and then you have to write an equation that relates the variables, and you have to make sure that your equation only has variables where you know the rate or you want the rate, right? So for us, we have the problem a fish is being reeled in at a rate of 1 foot per second from a point 15 feet above the water. At what rate is the angle between the line and the water? I'm going to call that X too. At what rate is the angle between the line and the water, which I called theta, changing when there is a total of 25 feet of line out? All right? So he's reeling the fish in, or she is reeling the fish in at 1 foot per second. Now, which dimension is changing at that rate of 1 foot per second? X. That's the rate that the fish is traveling in the water, but the person is reeling in line at 1 foot per second, so it would be z that's changing, right? So our first thing that we're given is dz dt, and does it equal 1?
Negative. No.
Negative 1.
It equals negative 1. That's getting shorter.
Yes, it equals negative 1 because your z dimension is getting smaller, right? Okay, this 15 right here, I didn't even give it a variable name. Why didn't I give this side a variable? Because it's a constant, right? This side is changing. So even though it says that there's 25 feet of line out, is that 25 constant?
No.
No, because they're reeling it in, right? It's changing. So we can't give it a constant label. But we can write down that this is happening when z is 25. Now the question says, at what rate is the angle between the line and the water changing? What are we looking for?
The angle, alright, sine is going to be like opposite over hypotenuse.
We're looking for d theta dt.
Alright.
And actually, Nelson, not to shoot you down, but what you're saying is exactly what we need next.
Hey,
okay?
Smart person here.
All right. So yeah, we're looking for we're given dz dt. We want d theta dt. So we need an equation that relates theta and z.
Cosine.
Okay. So cosine of theta would be x over z. And if we used that, suppose we wrote cosine theta equals x over z, then we need variables where we either know the rates or want the rates. We want d theta dt, we know dz dt, do we know dx dt? No. So let's try, is there a different trig function that we could pick? Sine.
Sine is so much better.
Okay, so if we pick sine theta is what over what?
Opposite over
Good. For this picture,
15 over z.
15 over z.
Cool.
All right, so sine theta works because the 15 is a constant. We know d theta dt and we want dz dt. Or we know dz dt and we want d theta dt, right? So we're good. Now, in order to take the derivative of this, I'm just going to rewrite this side as 15z to the negative first.
Hey.
All right, I want you guys to take a second and differentiate this equation. Differentiate both sides. Yes?
Would it be okay if you move the z to the other side and do the product rule?
Absolutely, if you want to do product rule. Sure. You know what else some people do that is really slick, that students don't think they're going to like, but no. Picking the reciprocal function, right? Because then you don't have any negative powers. It makes it an easier, right? So you could go with that, that's totally fine. But most students don't think that way. So we're going to go with this just because this is probably what most people would do. But if you want to go with this, it's absolutely fine. Right?
Is that pepper jack cheese?
Okay, so what's the derivative of sine theta?
Cosine theta.
Cosine theta
Times
times d theta dt, because we're differentiating with respect to time, not theta. So it's cosine theta times the derivative of theta, which is d theta dt. So here we get negative 15 z to the negative second times dz dt. So here's what we have, just cleaning it up a little bit. We have cosine theta d theta dt equals negative 15 over z squared dz dt. All right, well, let's plug in what we know. I know z is 25, right? I'm going to write it as 25 times 25. And then I know dz dt is negative 1. Cosine theta. I don't know theta, and I don't want to know theta. I don't need to know theta in order to find the cosine of theta. Because the cosine of theta, rather than actually finding theta and finding its cosine, instead I could think of it as side ratios on the triangle, right? Cosine of theta would just be adjacent over hypotenuse. So if this side is 15 and this side is 25, does anyone know what this side would be?
20.
This side would be 20. It's a 3, 4, 5 multiple, right? So the cosine of theta is what over what?
20 over 25.
20 over 25. So when you have to find cosine theta, or the trig value for any angle, if you've got the triangle with sides, use the sides. Don't try to find the angle itself, right? Just use the sides. All right, so d theta dt. So now we get a positive 15 over 25 times 25 times 25 over 20. The reason I keep it separated because a lot of times things cancel
What
really
about the
nicely.
negative?
Oh, I multiplied it together. And then here we can cancel a 5, we can cancel a 5, and we're left with 3 over 100. Now the units for trig, all angles in this class are measured in what? Radians. Doesn't matter what we're talking about. When you're doing calculus on this, that natural angle just, isn't it beautiful, just comes right out. So that 3/100ths, that's not degrees, that's radians per, in this problem, what's time in? Seconds. So this is saying that the rate of change of this angle is 3/100ths radians per second. Now what that's saying is that this angle is getting bigger. Does it make sense that the angle is getting bigger?
Yeah.
Yeah, right, because as the line reels in, right, the angle grows. Does that make sense? Okay. All right, so 3/100ths radians per second. Please don't put thetas per second, right? I have a lot of students who do that. It sounds funny, but it happens a lot where I'll get, like, students will put, like, thetas per second. Theta's not a unit. Theta's just a variable name, right? So it's not thetas per second, it's not angles per second, it's radians per second. All right? Okay. How does that sit with you?
Sideways.
Sit sideways? Is sideways good?
Could be.
It's sitting at an angle.
Inception.
Oh, that's fine. We're ready to change that.
These are horrible
Okay.
jokes. I'm sorry.
All right. So that problem is probably the most typical that you'll see when it comes to trig-related rates. This next one we're going to do is a little bit more unusual,
Looks like a pain.
but it does come up from time to time. So we're still going to do it, and it will be in your homework tonight.
I'm copying it down so that.
Okay, so take a minute, copy it down. Might want to leave like a line or two under each part if you like to do your work as you write. So we have a carousel. Yes, it is joy.
That's such a fast carousel.
Yeah. So has a radius of 20 feet and it completes one rotation every 30 seconds.
That's actually a slow carousel.
I was gonna say, I don't think that's that fast.
That's actually very slow.
Yeah.
It could be, no, that's very fast. I just take my time on
That
this
is
stuff.
ridiculously slow.
No, it's not. That's so fast. 20 feet? So what's the circumference? Pi r squared? Right?
That's the area.
Alright, so 2
Pi
pi r?
ID.
So wait, what's that? Like 2, 40 pi? I don't know how big that is. It's like 40 times 3, what is that? Like 120 feet? That's like half a mile. That's like that is so slow. Goodness. But that's so fast. Gosh darn it, you got me all confused.
That's
now.
like no.
You could get whiplash from that. I'd say let's forget the problem and start working on suing them.
Okay.
Is what I would say.
Maybe for like boredom.
I just realized this is on camera too. Oh dear.
So this carousel that has a radius of 20 feet and completes one complete rotation every 30 seconds, we want to find the angular velocity d theta dt. We are not going to use formulas to come up with the angular velocity. Rather than using formulas, we're just going to think about it and look at the expression that we have written here, d theta dt. It's the change in the angle over the change in time. So we have to think, well, let's see. We know that this carousel completes one rotation every 30 seconds. So could we figure out what the change in angle is for one rotation? How many radians does it pass through with one rotation?
2 pi.
2 pi, right? So what happens is this carousel travels 2 pi radians every 30 seconds, right?
That's fast.
Right? Okay, isn't it though? So our d theta dt would be 2 pi radians every 30 seconds, or pi 15ths if we want to reduce the fraction, radians per second. Nice constant rate. So notice in the first problem, the angle was changing and we were finding the rate of change of that angle, and it varied depending on the length of the line. Here, we have the rate of change of the angle, it's pi 15ths and it's a constant. If you were to ride the carousel for 10 seconds, what angle would you be at compared to where you started?
We just multiplied the velocity by 10.
Exactly. So if we travel pi 15th radians every second, and we did that for 10 seconds, how many radians would we pass through? Well, it would be 10 times pi 15ths. Isn't it though? Yes. Or reduced to 2 pi thirds radians from wherever you started. All right. Y'all good with that, or are there questions? This is the most important part, this part A. Right? You get this, you got the problem. Not really, but
You get the first part you got first.
okay. Because it says it does one rotation in 30 seconds, and then one rotation is one time around the circle. So you think, how many radians does it pass through? 2 pi, right? One time around the circle would be 2 pi radians. So it travels 2 pi radians every 30 seconds. So it'd be 2 pi over 30, because it's radians over seconds. So 2 pi over 30, and then we just reduced. All right, part C. Find dx dt as a function of theta. X is this horizontal component, right? It's the horizontal distance the horse is from the center. So the question we're finding right now is, we just want a general function for dx dt, where the input is theta. So we need an equation that relates theta and x.
Cosine.
All right, does anyone have anything else, or do you all agree on cosine?
I think it's obvious. It's cosine.
You could use tangent, that has x.
No, it
No?
doesn't.
It does, but why would you not want to use tangent?
It's cosine.
Secant.
Because we don't have the other one.
You don't know this y value, you don't know the rate of change of this guy, right? But the hypotenuse is nice. Why is that hypotenuse nice to
Never
use?
changes.
Because it's a constant. Whenever you can pick a trig function where one of the sides is a constant, go with that one, right? Because it makes the whole problem easier. So for this, for part C, we would write the equation cosine theta equals what over what?
X over 20.
X over 20. Now, do I have to use quotient rule to find the derivative of x over 20?
No.
No. What should I think of it as?
1/20.
1/20th x, right? All right, everyone find the derivative of both sides. Okay, so what's the derivative of cosine?
Negative sine theta.
Negative sine theta
D theta dt.
d theta dt equals x over 20. What's the derivative of that?
120.
1/20th
dx dt.
dx dt. Very good. Now, we have to solve for dx dt, so I'm going to multiply both sides by 20. So I get dx dt equals negative 20 sine theta d theta dt. Here's the problem. The problem said we want dx dt as a function of theta. These are actually two different variables, the theta and the d theta dt. So we can't leave a d theta dt in there, because that would make it a function of two inputs. So could I replace the d theta dt with something?
Pi 15.
Pi over 15, right? So I plug in the pi over 15, so I get negative 20 times pi over 15 sine theta. And just reducing, I get negative 4 pi thirds sine theta. One input, one output. So I plug in an angle, I get out the horizontal rate of change. Part D, find dx dt when t equals 10. This says find it when t is 10. Is t an input to our function? No. So how are we supposed to do it?
Plug the
That's it.
one from part D in.
Oh, so we need the angle that we're at when t equals 10. Look at that! Boy, lucky for us, we did that in part B, right? What? So in part B, we found out our theta value when t was 10 is 2 pi thirds. So for part D, your dx dt at t equals 10 is negative 4 pi thirds times the sine of 2 pi thirds. What is the sine of 2 pi thirds?
Root 3 over 2.
It is root 3 over 2. Positive or negative?
Positive.
Positive. So we end up with, just reducing a little bit, negative 2 pi root 3 over 3. What would the units be for dx dt?
Feet per second.
Feet per second. It's the units of x, which are feet, and the units of time, seconds. Feet per second. Yeah.
How do you know when to simplify the sine theta or cosine theta? Because in the first problem, we wrote cosine theta as 20 over 25, and then in the The second one we just left it.
Yeah, we didn't have enough information on the triangle to, when t equals 10 to know to use the triangle for it.
But if you had enough information, would you just?
You could go with the sides.
Okay.
Yeah. Yep.
Nah.